Welcome to G Fun Facts Online. In the silent, vast theater of the universe, the most spectacular dramas unfold on a stage so small and on a timescale so brief they defy imagination. We're used to thinking about the slow, majestic waltz of planets and galaxies, but within every single speck of matter, there's a frenetic, high-speed dance between the heavy atomic nucleus and its cloud of zipping electrons. Witnessing this dance, filming it in real time, has been one of the great dreams of science. How does a chemical bond actually break? How does light become electricity in a solar panel? The answers are written in the language of atomic motion. Today, we're exploring how science built a camera with a shutter speed so phenomenally fast it can freeze moments lasting less than a trillionth of a second. This is the story of two frontiers of time, two Nobel Prizes, and how we learned to film the complete motion of an atom. Our story begins on a timescale that is already profoundly difficult to comprehend: the femtosecond. A femtosecond is a quadrillionth of a second, or 10 to the power of -15. To give you some context, there are more femtoseconds in a single second than there are seconds in 31.7 million years. This is the natural timescale for the movement of atomic nuclei, the heavy protons and neutrons that form the core of an atom. Before the 1980s, the world of chemistry was a world of inference. Scientists knew what reactants they started with and what products they ended up with. But the actual journey in between, the fleeting ephemeral moment called the transition state where bonds are broken and new ones are formed, was a complete black box. It was like knowing that a caterpillar enters a chrysalis and emerges as a butterfly, but having absolutely no way to witness the miraculous transformation happening inside. To film this atomic transformation, you'd need a strobe light that flashed faster than the atoms themselves could move. The challenge was met by the Egyptian-American chemist Ahmed Zewail, who developed a beautifully elegant pump probe technique. Think of a sports photographer trying to capture the exact moment a bat hits a baseball. They can't just rely on reflexes. Instead, they could set up a system where the sound of the crack of the bat, the pump, triggers a high-speed flash, the probe, a microsecond later to take the picture. By repeating this process and slightly changing the delay of the flash each time, you could build a perfect stop-motion movie of the ball compressing and flying off the bat. Zewail applied this logic to molecules. He used an intense, initial laser pulse, the pump, to inject a burst of energy into a molecule and kickstart a chemical reaction. Then, after a precisely controlled delay of just a few femtoseconds, a second, much weaker laser pulse, the probe, would act as the flashbulb. It didn't drive the reaction further, it just took a snapshot of the molecule's current state by measuring how it was absorbing light at that exact instant. In a landmark experiment in 1987, Zewail and his team at Caltech used this method to watch the dissociation of a cyanogen iodide molecule. For the first time in history, they saw the bond between the iodine and the carbon atom stretch, vibrate, and finally snap, all over a span of just 200 femtoseconds. The elusive transition state was no longer a theoretical concept. It was an observable, clockable, molecular event. This groundbreaking work gave birth to the field of femtochemistry and deservedly won Ahmed Zewail the 1999 Nobel Prize in Chemistry. But while revolutionary, this pump probe spectroscopy provided an indirect view. It measured the light absorption, which is like seeing a molecule's shadow. From the shape of the shadow, you have to infer the structure of the molecule itself. This works well for simple molecules, but for complex ones, it's a challenge. The next logical step was to develop a technique that could directly image the positions of the atoms, like taking an X-ray instead of just looking at a silhouette. This led to the development of ultrafast electron diffraction, or UED. This method adapts the principles of an electron microscope to the femtosecond timescale. Instead of a probe pulse made of light, UED uses a pulse of high-energy electrons. Because electrons have a much shorter wavelength than visible light, they can resolve the positions of individual atoms within a molecule. The setup is conceptually the same. A femtosecond laser pumps the sample to start a change, and a time-delayed electron pulse probes it. The electrons scatter off the atomic nuclei and their surrounding electron clouds, creating a diffraction pattern on a detector. This pattern is a direct fingerprint of the molecule's geometric structure at that instant. By analyzing how this pattern changes as the time delay is varied, scientists can reconstruct a direct movie of the atomic cores, moving, vibrating, and rotating. UED has provided stunning insights, like capturing the ringing of a molecule's atoms after being struck by light. Together, these femtosecond techniques pulled back the curtain on the first act of the atomic drama, revealing the world of vibrating, reacting atomic nuclei. But the real instigators, the nimble dancers who spark every change, were still moving 1,000 times too fast to be seen. To capture them, science had to enter a new realm of time, the attosecond frontier. If the motion of atomic nuclei defines the femtosecond world, the motion of electrons defines the attosecond world. An attosecond is a billionth of a second, 10 to the negative 18. It is to 1 second what 1 second is to the entire age of the universe. When an atom absorbs light, when a chemical bond forms, or when electricity flows, it is the electrons that move first. These movements are the primary events that initiate all subsequent, slower changes in matter. For decades, filming this seemed impossible. The fastest lasers produced femtosecond pulses, 1,000 times too slow. But in a convergence of theoretical insight and experimental genius, physicists discovered a way to use those very same femtosecond lasers to forge the even shorter attosecond pulses they needed. This discovery was so fundamental that it earned Pierre Agostini, Ferenc Krauss, and Anne Lhuillier the 2023 Nobel Prize in Physics. The engine at the heart of this revolution is a technology called high harmonic generation. It's a bit like music. If you strike a single key on a piano, you hear one fundamental note. But if you strike it hard enough, you also hear a series of quieter, higher-pitched overtones or harmonics. In 1987, Anne Lhuillier and her colleagues found that when they focused an intense infrared femtosecond laser into a jet of noble gas, like argon, the gas didn't just absorb the light. It re-emitted a dazzling array of new light frequencies, all of which were high harmonics of the original laser frequency. It was like striking a single note and hearing a whole chord of higher-pitched notes ring out. But what was causing this? The answer came in 1993 from theorist Paul Corkum, who proposed an elegant three-step model describing a dramatic journey undertaken by an electron. Step 1. Tunnel ionization. The electric field of the intense laser pulse is so powerful that it actually warps the atomic potential holding an electron in place. The field creates a tiny tunnel through which the electron can escape its parent atom, a purely quantum mechanical effect. Step 2. Acceleration. Once free, the electron is grabbed by the oscillating electric field of the laser wave. It's first pulled away from its parent ion, gaining a tremendous amount of energy. Then, as the laser field reverses its direction, which it does every femtosecond or so, the electron is stopped in its tracks and accelerated violently back towards the ion it just left. Step 3. Recombination. The electron, on its high-speed return journey, slams back into its parent ion. This reunion is explosive. The electron releases all the kinetic energy it gained from its joyride in the laser field, in a single, brilliant flash of high-energy, extreme ultraviolet light. This entire three-step process occurs every half-cycle of the driving laser field. Each recombination burst lasts for only a few hundred attoseconds. And the key insight was this: if you could perfectly synchronize all these high harmonic light waves, they would add up to create a train of incredibly short pulses, an attosecond pulse train. In 2001, this theory became reality. A team led by Pierre Agostini in France not only generated an attosecond pulse train, but also measured it, proving they had created a series of light bursts each lasting just 250 attoseconds. Simultaneously, in Austria, a group led by Ferenc Krauss was pursuing an even more ambitious goal: to isolate a single, solitary attosecond pulse. A pulse train is useful, but for a clean experiment, you often need one starting gun and one flashbulb, not a rapid-fire burst. By developing techniques to control the shape of the driving laser pulse down to a sub-cycle level, they could ensure that the violent three-step process happened only once during the single most intense peak of the laser field. In 2001, they successfully produced and measured an isolated pulse lasting 650 attoseconds. This was the ultimate tool for filming the electrons dance. So with these pulses in hand, how do you actually see anything? The most powerful technique is known as the attosecond streak camera, or attoclock. Imagine you want to measure the incredibly brief time it takes for a photo to print from an old inkjet printer. Instead of a stopwatch, you could place the photo paper on a conveyor belt moving left to right at a known, constant speed. The ink hitting the paper at the beginning of the print process will land at one position. The ink hitting at the very end will land at a different position further to the right. By measuring the length and angle of this streak of ink along the paper, you can precisely calculate the duration of the printing process. The attosecond streak camera works on the same principle, but with electrons. An isolated attosecond pulse, the pump, hits an atom and knocks an electron out. This starts the clock. Simultaneously, the oscillating electric field of a much longer, synchronized femtosecond laser pulse acts as the conveyor belt. An electron released early in the laser cycle gets pushed in one direction. An electron released slightly later gets pushed in another. By measuring the final energy and direction of the streaked electron, scientists can work backward and determine with attosecond precision exactly when it was released from the atom. This powerful technique led to one of the first landmark results of attosecond science: measuring the time delay in photoionization. It had long been assumed that when light hits an atom, its electrons are ejected instantaneously. But using the attoclock, scientists showed that there is a tiny but measurable delay, on the order of tens of attoseconds, between electrons coming from different orbitals or energy shells within the same atom. For the very first time, science could resolve the internal timing of the quantum world. The true power, however, lies in combining these two worlds. Almost every important process in nature begins with an attosecond scale electron rearrangement, which in turn triggers a slower, femtosecond scale movement of the atomic nuclei. Consider photosynthesis. A photon of sunlight is absorbed by a chlorophyll molecule. The initial event is the excitation of an electron to a higher energy state, an attosecond process. This rapid charge separation then initiates a cascade of chemical reactions involving the movement of entire atoms, femtosecond processes, that ultimately converts light into chemical energy. Or human vision. When light enters your eye, it strikes a retinal molecule. The absorption of the photon causes an electron to redistribute, triggering an incredibly fast change in the molecule's shape. This is an electron-driven attosecond event that leads to a structural change in the molecule, a femtosecond event, which then sends a signal to your brain. To get the complete picture, scientists now use combined experiments. An attosecond pulse might start a process by exciting an electron, and a delayed femtosecond pulse then probes the subsequent structural changes in the molecule's core. They can create a holistic movie of a quantum process. They press play with an attosecond pulse, watch the electron dynamics unfold, and then see how that initial electronic jolt translates into the physical movement of atoms that defines a chemical reaction. The black box is finally wide open. This has opened a floodgate of discoveries. Scientists have used attosecond pulses to watch an electron hole, the vacancy left after an electron is removed, migrate along a molecular chain. This is the most fundamental form of charge transfer, and watching it in real time is a crucial step towards designing more efficient molecular electronics in solar cells. It's also opened the door to light-wave electronics, where the flow of electrons in a circuit could be controlled not by a voltage, but by a light field, potentially enabling processing speeds 1,000,000 times faster than today's computers, operating in the petahertz range. The future of this frontier is dazzling. Scientists are working to generate even shorter pulses, pushing into the attosecond regime, which could one day allow us to observe processes inside the atomic nucleus itself. There's potential for medical diagnostics, where the way light scatters from a blood sample could reveal the minute molecular changes that are the earliest fingerprints of disease. And perhaps the most tantalizing prospect is controlled chemistry. If you can watch exactly how an electron initiates a chemical reaction, the next step is to control it. By sculpting the light field that interacts with a molecule, scientists hope to one day wield a molecular scalpel, selectively breaking specific bonds to steer chemical reactions towards desired products and away from unwanted byproducts with unparalleled precision. The scientific quest for resolution has been a race against time. From the ponderous movements of planets to the frantic vibrations of an atom's core, and finally to the impossibly fast leap of an electron. With the advent of femtochemistry, we reached what felt like the finish line for chemistry. But the Attosecond frontier revealed a deeper, faster race course beneath. Today, we stand at a remarkable juncture. The tools of femtosecond and attosecond science have given us the ability to create complete 4D movies of the atomic world, resolved in 3 spatial dimensions and 1 time dimension. We can now watch the entire drama unfold, the initial spark of an electron's movement, and the subsequent, slower dance of the atomic cores that it ignites. We can move from being passive observers to active choreographers, using light to direct the flow of energy and matter at its most fundamental level. The quantum movies we are now recording are not just scientific curiosities. They are the blueprints for the technologies of the future, promising revolutions in computing, energy, medicine, and our fundamental understanding of the universe itself. Thanks for listening to Fun Facts Online.